Hello everyone. In this video we're going to look at the concept of angles in standard position. So consider that we have a point, -512, on the terminal arm of an angle theta in standard position. So standard position is set in the coordinate plane. We have a point, -512, so that point would be somewhere around here. And that is on the terminal arm. Now an angle in standard position always has its vertex at the origin. So the terminal arm connects these 2 points. That's the terminal arm. The initial arm is always the positive x-axis. So theta is an angle of rotation between these two locations. So we consider that that terminal arm is revolving, rotating, tracing a bit of a circle. And theta is that rotation. So the most direct way would be simply to go like that. That's considered a positive angle. Now, in theory, I could have a negative rotation. So my negative rotation could go like that. Or I could have actually multiple rotations. So let's say I have 1, 2, 3 full rotations before eventually settling into that terminal position. That could be theta. I don't actually know how many full rotations are involved or if theta goes in the positive direction or not. It doesn't really matter for the exact values that we're asked to give. So we're asked to give the exact values of sine theta, cos theta, and tan theta. All of those angles that I drew are what are called coterminal angles. Coterminal angles are different rotations that end up in the same spot. So different rotation, same terminal arm. And they will all have the same values of sine, cosine, and tangent. So that would be, for example, this is an angle. I could have this as an angle, or I could have same terminal arm. I could have several different rotations and then end up in the same place. Those are all coterminal angles. In order to make some sense of sine, cosine, and tangent in an angle that isn't inside of a right triangle, we can draw a reference triangle. So our reference triangle is going to be the right triangle we can draw between the terminal arm and the x-axis. If my angle was already acute, so if I had an angle over here, for example, then the reference triangle would just be an acute triangle and theta would just be an acute angle inside of it. But in the case where I can't draw theta inside of a right triangle, I draw a reference triangle and then we have a reference angle. So theta, I've used alpha here to represent the reference angle. The reference angle is an acute angle always between the terminal arm and the x-axis. So you'll always be able to draw a reference angle inside of a reference triangle. Now what we do is we allow sides of this reference triangle to be negative depending on the quadrant that we find ourselves in. So in this case, we have a terminal arm in the second quadrant where x values are negative. So we're going to consider that this adjacent side of the triangle, the side that's adjacent to the alpha, to the reference angle, we're going to let it have a length. It's not really a length, but we're going to call it a length of -5. And the opposite side is going to have a length of +12. This hypotenuse I'm going to call r to indicate that it's the radius of the circle that is being formed by this rotation. And we can find r by using the Pythagorean theorem. R squared equals -5 squared plus 12 squared, which when you solve for r means that r equals 13, and we're going to let r always be a positive value. So the adjacent side or the opposite side could be positive or negative depending on the quadrant, but r is always going to be positive. Now that we know the lengths of all the sides of the triangle, we can simply say that sine of theta is going to be the opposite, which is 12, because that's opposite the reference angle, over 13, which is the hypotenuse. The cosine of theta is going to be -5, because that is the adjacent side, divided by 13. And the tangent of theta is going to be 12 divided by -5. More likely, I'm going to write that as -12/5, but either one is acceptable. So notice that I never need to know what theta is in order to say what its sine, cosine, and tangent are here. That's going to be helpful in the next example. So I have an angle theta in standard position, and I'm telling you that its sine is -3/7, and I'm telling you that it is between 180 and 270. So right off the bat, I know that theta actually doesn't involve a negative rotation, so I have to go in the positive direction. And it doesn't involve multiple rotations because it isn't bigger than 360 degrees. So theta is in the third quadrant because that's the quadrant where I would find angles between 180 and 270. And therefore, its reference triangle is this triangle in here with the x-axis, and the reference angle will be this angle right here. I never actually need, in this case, to find the measure of that angle because I have enough other information. If I know one of the ratios, sine theta in this case, I can find any of the other ratios. Tangent theta is the one I want. But I don't need to know what theta is. What I need to know is that sine is opposite over hypotenuse. The hypotenuse, I'm going to always let it be positive. So the hypotenuse here would be 7, which means that the opposite side has to be -3. That makes sense because my y value has to be -3 in the third quadrant. My x value also has to be negative because of the quadrant I find myself in. But I can find x using the Pythagorean theorem again. So x squared plus -3 squared equals 7 squared, or x squared plus 9 equals 49, which means that x squared equals 40. When I take the square root, because I know x has to be negative, I'm going to take the negative square root. So the negative square root of 40. And then I'm going to simplify that, knowing that the square root of 40 is the same as the square root of 4 times the square root of 10, and 4 is a perfect square. So this gives me -2 root 10. So the length of x is -2 root 10. Now that I know that side length, I can find the tangent of that angle. The tangent of theta is the opposite side, which is -3, divided by the adjacent side, which is -2 root 10. So now I'm just going to simplify that a little bit. Negative divided by a negative is positive, so I'm going to just turn this into +3 over 2 root 10. And then I want to rationalize the denominator, so multiplying by root 10 over root 10, we end up with the fact that the tangent of theta is equal to 3 root 10 divided by 2 times 10, which is 20. So if an angle has a sine of -3/7, and if that angle is between 180 and 270 degrees, then the tangent of that angle has to be 3 root 10 over 20. And finally, the other thing that we can use angles in standard position for is to find the exact values of certain special angles using the special triangles that we learned about last semester. So I have an angle of 315 degrees here, and I want to know its sine. So the first thing I'm going to do is sketch it. 315 degrees is going to end up in the fourth quadrant. So theta, in this case, 315 degrees, is that kind of rotation. The reference angle is therefore going to be this angle right here. And because of the quadrant that this is in, I can find the reference angle by taking 360 minus 315, so 45 degrees. How I calculate alpha will depend on which quadrant I'm in. So I just always make the sketch and look at it. My reference triangle is therefore this. But I know a right triangle with a 45-degree angle is an isosceles triangle. So I'm going to let the side lengths be 1. The x value is +1. The y value therefore has to be -1. And from Pythagoras, I know that that hypotenuse, or the radius of this circle, has to be, so the circle is this thing, the radius of this circle would have to be the square root of 2. And therefore, I can say that the sine of 315 degrees has to be the side that's opposite the reference angle, which is -1, divided by the hypotenuse, which is the square root of 2. Rationalizing the denominator, we find that the sine of 315 degrees as an exact value is -√2 divided by 2. It has the same absolute value as the sine of 45 degrees because that's the reference angle, but whether it's positive or negative will depend on the quadrant.